Now, we will start from the Ising model this class. In previous class, we deal with ferromagnetism, antiferromagnetism, and ferrimagnetism in terms of Weiss molecular field model. Actually, Weiss molecular field model is not an exact theory. We already discussed for that. If we consider for the molecular field, the molecular field itself is extremely high in order to describe the existing magnetic ordering. Instead, and the basic concept for the high molecular field, the origin come from the exchange energy, which is discussed in the Heisenberg model, but not explicit theory. It does not exist. Not exist. I mean that I did not mention for the exact theory for the magnetic ordering. Basically, it is very difficult problem because the Ising model is the simplest model to describe the magnetic ordering, which deals with the spin up and spin down state. Very simple to describe. But anyway, then I will show that the one-dimensional Ising model do not describe the magnetic ordering because there is no spontaneous magnetization in 1D spin chain. In the 2D spin chain is the Angsaga solution, Angsaga problem, and the two-dimensional problem is very complicated and is extremely complicated because physicist Angsaga resolved the problem in two-dimensional square lattice, Ising spin lattice, and he successfully described for the spontaneous magnetization, and he awarded Nobel Prize. Then it was very difficult problem, and until now the three-dimensional problem cannot be solved until now. And if you succeed to calculate the three-dimensional Ising model, and you may get the Nobel Prize. Yeah, and I hope that somebody who take this course can resolve the problem for three-dimensional Ising model. And anyway, I will describe for the basic concept and the basic definition of the Ising model. Ising is also name of physicist, and just only then the ferromagnetism is a spontaneous polarization of magnetic spin in the same direction at below the Curie temperature. And here the Ising model is a simple model, and there are two possibilities. One is spin up and spin down. They do not consider for the spin precession or the spin reorientation and the canted spin system, and it is a very simple model. A system that an array of n fixed points, we call it as a lattice site. It is a lattice site from an n-dimensional periodic lattice. N-dimensional means that it is a one-dimensional, two-dimensional, and three-dimensional. And also important thing is that the spin only spin up or spin down. Is a spin up case and a spin down. At each spin site state, and they do not consider for the spin canting or the spin precession and the spin reorientation or the anyway very complicated spin structure can exist in real system, but in this in this Ising model only consider for the spin up and spin down. That is the simplest model. And it is reasonable because the ferromagnetism and antiferromagnetism and ferrimagnetism, the basic model describe only for the spin up and spin down state, which we call spin polarization, spontaneous spin polarization. And here, in this case, the energy on this Ising model, energy for the Ising model energy as a subset of the spin system is that the first term is the Heisenberg model, Heisenberg Hamiltonian for each spin ij. Nearest there is we only consider for the nearest neighbor interaction, and also epsilon ij is the interaction energy, and si sj. Basically, it is a vector, but in this case, then the scalar is enough. Because scalar is enough because we only consider for spin up and spin down state. Also, when you apply the magnetic field, and here for n lattices, this is the external. It is the external magnetic field. And also, it only consider for the nearest neighbor interaction. That's why this term has the here n number of lattice sites, and the gamma is the number of nearest neighbors, and 1/2 to avoid double counting. And there are 1/2 in gamma terms, and also here n is the number of lattice sites, and the gamma is the number of nearest neighbors. And for example, in the 2D square lattice, in the 2D square lattice case, one spin state and here square lattice. If we think about at the origin atoms at origin, and the interaction can have the 4 degree of freedom, and therefore the 4 in the 2D square lattice. And also in 3-dimensional simple cubic structure, this is a simple cubic structure. And if we consider for 1 atoms at a site, 1 atom in here, and the nearest neighbor 1, 2, 3, 4, 5, 6. There are 6 nearest neighbors in the 6 nearest neighbor in 3-dimensional simple cubic. Another one is that BCC case, and here BCC means that simple cubic structure, and the atom inside here. In this case, the 8 number of nearest neighbors in the upper side, 4 number of atoms in the upper side, and 4 number of atoms in the lower side. There are 8 number of nearest neighbors, 8 number of nearest neighbors in the 3D BCC body-centered cubic structure, BCC lattice. And therefore, gamma is the number of nearest neighbor, and n is the number of lattice side, and 1/2 is for the considering for the double to avoid the double counting. And also, it is reasonable to assume that isotropic interaction in isotropic interactions, the interaction energy can be regarded as a constant value. And therefore, the Ising spin Ising model energy for spin state is the minus epsilon for ij for nearest neighbor interaction, SISJ minus h external magnetic field for NSI. As you know, and epsilon, if the epsilon is positive, it is ferromagnetism because ferromagnetic spinel alignment in the same direction is energetically favorable, and for negative energy, it is the antiferromagnetic moment. Antiferromagnetism is preferred, and it is Heisenberg model. In this class, I assume that you are familiar with quantum mechanics and statistical mechanics. And in the statistical mechanics, you know the thermodynamic parameters can be calculated as following formulas. And we use that thermodynamic parameters. And in the statistical mechanics, partition function is very important. And there are two configurations. One is the grand partition function, and the other one is the partition function. And canonical ensemble. There are two ensemble: canonical ensemble and the grand canonical ensemble. Canonical ensemble is there is only energy exchange. Energy exchange between the system and the reservoir. And also in grand canonical ensemble, the energy and particle exchange. And energy and particle can exchange between the system and with the reservoir. And also particle exchange energy, we call it as a chemical potential. It is chemical potential. Chemical potential is the energy for driving force of particle moving from one side to the other side. It is a particle. It is a chemical potential. And here we only consider for the partition function. We only consider in the grand canonical ensemble because in magnetics in solid state the energy only exchange and there is no particle exchange. In some cases, especially for electrons can exchange the particle, but in the spin system, spin is, if we assume that spin is localized in Ising model, and therefore we only consider for the energy exchange. Therefore we only consider for the canonical ensemble in here. And also, therefore, we consider for partition function. Partition function, I means that the Ising model, it is a function of the magnetic field and temperature. And the Boltzmann factor is that exponential minus beta energy for spin system. Therefore, in this case, the V summation for the spin 1, and spin 2, and so on, spin n, and spin is that has a plus minus 1, and two spin up and spin down stage, and therefore it is there are for each spin lattices, and here there are 2 to the n terms. Yeah, here. And if we know that partition function, then the other many physical properties can be calculated like the formula and the Helmholtz free energy. Helmholtz free energy. Anyway, magnetic field and temperature minus kBT ln partition function. It is Helmholtz free energy and internal energy. Internal energy is that minus kBT square partial T Fi over kBT. It is the internal energy, and heat capacity Ci HT is that temperature derivative with internal energy. It is heat capacity, and importantly in magnetic materials and magnetization. Magnetization is that M is the negative field derivative of the free energy. Yeah, it is a magnetization. And anyway, and here the when you consider for the spin system, and also for applying magnetic field, it is spontaneous magnetization. Actually, for without magnetic field, the energy Ising spin for energy is zero because of the cancellation of the spin configuration and spin up state and spin down state. Spin up state for the spin up state and spin down state. Anyway, then in antiferromagnetic system versus temperature, and even though at zero magnetic field, if the spontaneous magnetization is occurred and there is spontaneous magnetization, but in their spin up state and spin down state, and symmetrically evolves for the magnetization. Therefore, it is a zero field case. We call it as a TC. Then anyway, it is a magnetization, and also it is a saturation minus saturation magnetization. By applying magnetic field also, and smearing out the magnetization, like this. Like this. And I will show that in Ising model there is no spontaneous magnetization in one-dimensional system, and because the interaction between the nearest neighbor so weak in one-dimensional case, because there are only two nearest neighbor, but in two-dimensional spin system there is a finite spontaneous polarization, and because the full number of nearest neighbors, and therefore, and here I do not introduce the two-dimensional Ising model, because the Angsa solution is very difficult, and also difficult to understand, and Angsaga awarded Nobel Prize for the exact calculation. Instead, we will deal with mean field theory and some approximation, like for example, Bragg-Williams approximation and Pierce approximation. And we need some approximation is needed in the statistical mechanical point of view, I will go on the Ising model mean field theory.